In this video, I'm going to discuss about what is quantile regression and how is it different from the linear regression. Okay. All right. To understand what is quantile regression, we will take a case first, and then we'll go to the theory and we'll see how we can interpret a quantile regression. Okay, and how is it different from normal linear regression. Okay, so here is a case. Uh, we want to uh, uh, we want to try to understand how the birth weight of infants is getting impacted by some of the predictors like gender, marital status of the mother, and the smoking status, whether the mother smokes or not. Okay, so these are some of the predictors for the infant uh, weight. Okay, so in order to model uh, that relationship, we use a linear regression. So the linear regression looks like this. Okay, weight is a function of gender, smoking, and marital. Okay, and we have got the coefficient, slope coefficient, as well as the intercept. um, all right, so that's a linear regression model, right? Well, can this model explain certain aspect about this relationship? So what if we ask this question: does gender affects differently uh, for low weights and high weights, right? So for the lower weights and for the higher weights, that means for the lower percentile in the population and in the higher percentile of the population, how does gender affect? Does it affect differently? Does the beta 1 value takes a different value for lower percentile of the population and higher percentile of the population? In linear regression, that cannot be explained because beta 1 is always a constant in linear regression, right? So this is constant. This doesn't change. This doesn't change with respect to whether you are talking about the lower quantile or the higher quantile. So in order to understand this kind of relationship, we need to use the statistical model known as the quantile regression model. And in this particular video, we're going to learn what is the theory behind quantile regression model and how is it used. All right. So quantile regression is a kind of model which models the conditional quantiles of the dependent variable, and we'll try to understand what is a conditional quantile. Okay. So how is it different from the ordinary least square based regression model? The ordinary least square based regression model, or the OLS regression model, models for the conditional mean. So what we find out in OLS is that we find out the mean of y given the x variables, right, and the beta, right? We find out the conditional mean, right? In the case of quantile regression, we just replace that with median, or we just replace that with quantiles. Okay, y quantile, okay, given the xi values, okay, or the predictors or the cofactors, right? And quantiles can be any number of quantiles. It could be the first quantile, the fifth quantile, 10th quantile, 25th, 50th, 90th. So you can have multiple regression models for the same data. Whereas when you take the average, you just have one average, right? But quantiles could be many in a data set. Remember the problem we talked about in the case that we took in the first slide. There we were not able to find out the impact of somebody or the mother being the child being male and female. How does this weight get affected with respect to the different quantiles in the data, or different extremes of the data, in the lower extremes and in the higher extremes. Similarly, some other variable could be how does smoking habit of the mother impacts child weights in lower quantile and in higher quantile, or in the lower set of observations in higher set of observations. Okay, and observations are, let's say, ordered um, with in terms of their weights. Okay, and that can be explained if one fits quantile regression, which fits several models in this data, and hence is able to find out a better fit, because it fits differently for different quantile, or quantile can be fixed at one point and then regression can be done. Okay, so we'll take an example of where we'll plot it out so that it will be more clear. Okay, so in certain cases, more than the mean or more than the average value of the dependent variable y, it is the lower quantile and the higher quantile that are of more interest to us. Especially in the nutrition or the body mass index study. Okay, where people with obesity and people with malnutrition are of more interest to the researchers. Why so? Because these are the two problems. Obesity is a problem, malnutrition is a problem, right? Hence, if you average it out, then you will feel that it's average. For example, the weight of an infant is, let's say, 35 kg, which is some sort of an obesity, and the other one is 12 kg. If you take the average, it is going to come out to be somewhere around 20 kg, which is a normal weight. So linear regression is not able to capture the the pattern, or the um, situation, or they are in the extreme values, right, in the lower extreme as well as the upper extreme. Okay, so here is an example. Okay, so we're plotting the body mass index, BMI, or the body mass index. Okay, so that's nothing but I guess the weight by height, something like that. Okay, I'm not sure. So it's something to do with the weight and the height of the infant, or of a person. Okay, and there is some sort of a limit to for body mass index, which says that somebody is fit, somebody has a good weight height relationship. Okay, proportionate weight for height. Okay, so that is the idea behind body mass index, and you can read about it more about it in Wikipedia. Okay, so here is the distribution of body mass index. You can see the body mass index improves at a very fast rate for the initial years of somebody, right? So in the initial years, it improves, or there is a steeper increase in the body mass index, and then it stabilizes. It stabilizes, right? So in the middle ages, it stabilizes. There is hardly an increase, and then at the in when somebody gets old, the body mass index comes down further. Okay, and that's a typical pattern that one can find in the nutrition study. People doing research in nutrition study, they are more interested in finding out the relationship of different factors with respect with body mass index in the this particular period, and this particular period, and this particular period. Okay, so the initial year and the end years. Okay, how does it affect in the when somebody is a child and growing up till teenage, and how is it affecting after age of 60 and somebody is old. Okay, the middle years are of less importance to them. In these particular cases, linear regression may not be a suitable thing. Okay, and what interesting in this case is that for different quantiles, the rate of growth or rate of change of um, body mass index, rate of change of BMI with respect to rate of change of the age is different, right? It's different. Sometimes it's steeper, sometimes it's less steeper, and so on. Same with the right hand side quantile. Same with the higher quantiles, right? It could change, right? So in this situation, the quantile regression is more suitable than the normal linear regression. Okay, so all these lines are for different quantile, for quantile 1, quantile 2, and quantile 3. Okay, it could be 25th, 50th, and 75th, and so on. So this could be 25th quantile, and then this could be the green one, and it could be 50th quantile, and this could be 75th quantile. You'll see the rate of change is different for all three quantiles, and that is of interest to the researchers in this case. So let's learn a bit about the theory of quantile regression and how the coefficients are estimated in quantile regression in contrast to the OLS based linear regressions. Okay. So we'll try to compare the OLS with the quantile regression. So what happens in OLS? We minimize the error sum of square, okay, and we find the optimal value of beta naught and beta 1, which minimizes the error square, right? Sum of the error square, right? Where E is the error. So how do we find the error? The dependent variable yi minus beta naught plus beta 1 xi, and this is estimated one, okay, and then when you take the difference of that, you find the error, because this is the estimated one, this is the actual one. When you take the difference, you find the error, you square it, and then you minimize it, and for what value of beta naught and beta 1 this is minimum, that's what is taken as the final value of beta 1 and beta 1 and beta naught in the regression, right? Or that's the output from this OLS based regression. What happens in least absolute deviation equation, right? Least absolute deviation equations. We replace the square with the modulus, okay, and rest is same. Okay, we minimize the error in such a way that we minimize the error without taking the square. We just take the modulus of that, right? And that happens in least absolute deviation way of doing a linear regression. Okay, quantile regression is an extension of the LAD with bit of a change with that. So we introduce a penalty term Q or theta, whatever you call it, penalty term. And so what the idea in quantile regression is not to find the conditional mean of the dependent variable. It is the conditional quantile. Okay, so if you want to predict the 0.5 quantile, so 0.5 quantile is nothing but the median. Okay, the median. Okay, you want to find the median, regression at the median. Okay, so it will be exactly at the quantile value will be 0.5. Similarly, it could be 0.25, 0.75, and so on. The penalty factor penalizes for under prediction, and it also penalizes for over prediction, right? So that it stabilizes for that particular quantile. Okay, so that penalty factor is an additional factor in the quantile regression as compared to the least absolute deviation equation. And the error term that we have written here is nothing but yi minus beta naught plus beta 1 xi, exactly same as what is there in OLS. Okay, all right, so when we substitute it or substitute the terms, and how does the the quantile regression estimation look like? So here is it. So this is more elaborate. So we minimize this particular function, the entire thing, such to find out the beta naught and beta 1. Okay, we have the penalty term, we have the error, so this is the error term, this is also error term in this case, and this is the penalty term. Okay, so this Q is the penalty term. Let's say it is used for penalizing for 25th percentile. So 1 minus q would penalize for the rest part. Okay, so if it is 25, the rest part will be the 75 percentile in the other side, right? And that's exactly why it is 1 minus q. Okay, uh, so so how does we find out the beta naught and beta 1? So in OLS we find out by OLS we can find out the solution very easily by using the least square method of doing it, by differentiating it, or we can also use the maximum likelihood estimation. Whereas quantile regression cannot be estimated in that way. One can estimate the coefficient for quantile regression by using the linear programming. Okay, so one can use an integer point algorithm or some sort of a simplex algorithm to be able to find out the coefficient beta naught and beta 1. Alright, so how do we interpret the coefficient that comes out from the quantile regression? That's important to learn here. Okay, it's very similar to what we do in ordinary regression, whereas certain things has to be understood properly. Alright, so we'll take an example to understand how the coefficients can be interpreted similarly and differently in linear regression and quantile regression. Marginal effect is interpreted similarly. That means if beta value or beta 1 is, let's say, 0.3, then we say that okay, the dependent variable goes up by 0.3 every time this particular variable goes up by 1, given other variables are constant. Okay, so that's how the marginal effect, and it's same interpreted similarly. Okay. However, quantile regression behaves differently because it has different estimates for different quantiles, and you can have as many quantiles you want for the regression to estimate, right? You can have so here is a case, and let's understand. So we'll take the first case that we had taken in the first slide in the beginning itself. Okay, so we wanted to find out the infant weight, which is a factor of which is a function of somebody is married, whether the mother is married, whether it's a boy kid or it's a girl kid, and whether the mother is smoking. Okay, these are the predictors for weight of the infant. Okay, in the linear regression, it predicts that the intercept is 3400. If somebody is married, then the weight of the baby goes up by 161. Okay, that's the difference, right? On an average, the weight of a boy, weight of a kid or an infant born to a married woman compared to the unmarried woman, the difference of weight is 161. Similarly, the average, or on average, if he is a boy, then the infant weight is 111 more than the girl. And if the mother is smoking, on an average, it's like you get like 89 kg or 89 kg less weight, 89 units. Okay, it may not be in kg, 89 units less than if the mother is not smoking. But does that say, or if you go back to the same question, does it happen the same for all the quantiles? It could be different. Okay, so we took the same regression, quantile regression, for 5th quantile, 10th quantile, 50th and 95, and let's compare. Let's compare what happens in the 5th quantile. If you look at the 5th quantile, the weight goes, the difference between a married woman and unmarried woman giving birth to a child, the weight in the child, the difference in the weight between these two categories is 200. That means the linear regression in this case is underestimating. Okay, if you go to 10th percentile, It's very similar, but again it's underestimating. It's 161, here it is 181. The fifth quantile it's 200. For the 50th quantile it's 120. The difference is 120. That means the linear regression is overestimating. And similarly for 95th quantile it's 80, which is again the linear regression is overestimating for 95th quantile. If you go to the next predictor, whether he's a boy or a girl, on average it's 111. The difference between a girl's weight and boy's weight is 111, given other predictors constant. But in fifth quantile, the difference is only 26. Whereas in the 95th quantile, the difference is 186. That means for the fifth quantile, it's underestimating. Whereas for the 95th quantile, the linear regression is overestimating. So that underestimation and overestimation for different quantile is an issue with linear regression. And if the extreme quantiles or the given quantiles are of interest to the researcher, linear regression is not a suitable way or suitable model to model this data. So one should go for quantile regression in this case, so that you can find different estimates for different quantiles, and some of the quantiles could be of interest to the researcher, like fifth quantile, which is the lower quantile, 95th quantile, which is the upper quantile. Okay, so that's how you interpret the coefficient of linear quantile regressions. What are the advantage of using quantile regression over linear regression? Okay, the first one is it's robust to the outliers. Okay, unlike linear regression, which get badly affected by outliers, quantile regression estimates are more robust, or the coefficients are more robust to the outliers. Okay, and whenever you have not so good data, which doesn't fit your distributional assumptions, like normal distribution and all, in linear regression, quantile regression gives a better fit. Okay, and because there is a flexible distributional assumption in the case of quantile regression. If your data is heterogeneous or some sort of heteroscedasticity is present in your data, quantile regression gives better results than linear regression. So whenever you have data which is, sometimes it's very close, the variance is less, and then sometimes the variance is very high. Okay, then in that case, quantile regression is a better fit to the data over the simple linear regression. Alright, thanks for watching this video, and please subscribe to our channel for more videos, and please also visit our website, which is there in the description section of this video. Thank you so much. Thanks for all the support.